let me know. We have a very similar examples in our lectures. If you attend the if you come on the lectures, probably we have very exactly the very similar examples, very simple examples that we have. It says that confirm the form factor one steel handbook 310 UB32 and then determining the section capacity NS. So we have two questions. We need to find form factor KF. We need to find the form factor KF. Second questions, we need to conform our answer to one steel, and we need to have a calculate the section capacity. And yes, okay, those are the three things that we need to do it. Now, for the form factors, the equations is given here. The form factors equation is close 6.2.2 on page number 87 on section 6. Form factor is equal to effective area and gross area. Is basically saying that effective area of gross area. Now this effective area and gross area business, that's saying that KF has two options. You can take KF equal to 1 or you can take KF less than 1. What is KF equal to 1? KF equal to 1 means that you don't have any local buckling. All the full section is fully effective. It is called fully effective. In the other sense, you can have effective area equal to gross area. So then it is become KF equal to 1. It is also sense that it is made of thick plate. It is made of thick plates, meaning that no local buckling occur. Local buckling will occur. You can't avoid. You can't make the sections which are fully rigid, but the buckling occur after yielding, and that's what we wanted. We want to yield the section first, and then the buckling occurs. The buckling will gonna occur. You can't just say that I have a steel members which will not deform. It will deform. It will buckle, like you have seen in the lab that it is buckle. But what buckling gonna happen? That will do it after yielding. We want to utilize the materials. We want to utilize the materials, meaning we want to get the capacity. Like if I draw it up here, this is the yield strength, let's say 300 megapascal. That is the yield strength here. If it is buckle before, at this point, then we can't just go this one. We need to take 150 megapascal. See, no good, because we want to use this 300 megapascal. So buckling should occur somewhere here. We are happy. If buckling occurs here, we are not happy. Right? So that's what the, so this KF equal to 1 comes here, that buckling will occur, but it's after yielding. And these ones, we have a KF less than 1, right? So the KF less than 1, then it is made of very thin plates. Like this, right? And then you have a effective area we need to calculate, and it is made of thin plates. And there is local buckling occurs after before yielding. So I hope it is makes sense. The story about the KF, it's not just you blindly follow the equations, but you know what is physically means that they talk about. So for that case, we need to take because they have given you this universal beam where you have a flange. That is your flange. So let's work on the flange first and do the check on the flange whether it gonna give you the slender sections or not, or compact sections. So we can calculate the lambda E value for this B on T, Fy on 250, right? And where these equations come from? These equations come from, and that is called plate element slenderness on this close 6.2.3 lambda E B on T, Fy on 250. That is for flange. Now, how do we get the thickness? Thickness of the flange, we can get it from the one steel tables. Now, thickness of the flange, one steel tables. What was the cross sections? Can someone? What is the cross sections? What is the beam size? UB, which one? 310. Yep. And the 310. 310, 32. You with me? Yep. And then in that one, thickness of the flange is 8 millimeters. So the thickness of the flange is 8 millimeters. Now we need to calculate this B. Now the B business can be done from here. Right? That's the B that you can calculate from here. The straight away the one steel table is already given to you, but this B that you're going to calculate, probably you know this distance, how much it is. That is 149, I believe. So that is 149. So if I want to calculate B, 149 take away 2, and this one is your thickness of the wave, 5.5. 5.5. So 5.5 divided by 2. Can you please use the calculators and tell me what is the answer? 149 divided by 2. Take away 5.5 divided by 2. $71, 75. Okay, so 71.75. So B on T equal to 71.75. Thickness of the flange 8. How much it is? B on T ratio. Please do the calculations. $8.96. We can check it from our one steel tables as well, that we have a 8.97. Look at here. That is given here, B by 2 and that thickness of the flange. Right? All right, so here we have 8.97 that you can pick 8.96, still rounding off, still okay, 8.97. Right, so we can take 8.97. So lambda E is equal to 8.97 square root for the flange. We have 310 UB, 320. So we can take 320 on 250. Can you please do the calculations? 10.15. So lambda E, and then if it is lambda E less than lambda EY, we said no buckling in the flange. And if lambda E is greater than lambda EY, we say that buckling occur. Okay, now what is lambda EY? How do we get the lambda EY? We can come back here in these tables. That is the table 6.2.4. And in these tables, we're not working with the circular hollow sections. We are working with the flat, because you look at this. This flange is flat, right? This is the flange flat plate. So it's flat. Longitudinal is supported at one end, outstand. So that is talking about flange, because you can look at this one here, that this longitudinal edge here, is fully supported. So if you look at the on this one on the screen, so this longitudinal edge is fully supported, and this is the outstand. That's what they talk about. One longitudinal edge is supported, and that is your flange. And here all this notation given: stress relief, hot roll, cold form, lightly welded. All your one steel tables, one is the hot roll. So that is HR. And for that case, yield tenderness limit is 16. Okay. So yield tenderness limit is 16. So lambda E is 10.15 lambda E, which is less than lambda EY. So which is 16. Therefore, flange will not buckle. Right, full flange will be stay as it is. Right, if it is greater relationship, we need to calculate the effective weight. But here we have a flange is fully effective, meaning that if you have a flange, this flange will be fully, the area would be fully, this area would be fully effective. If the buckling occurs, the buckling will gonna occur like this. Buckling will gonna occur like this. Wave. One longitudinal is supported, second longitudinal is supported. So this is wave. In the case of wave, both longitudinal edge is supported. Flange, if you have both, then you have one here supported. This is free edge. Okay. This edge is not supported. The flange has two longitudinal edge. One is here, another one is here. This end is free. Free meaning this is free to buckle. So therefore, it is one longitudinal edge is supported. Yeah, this edge is not supported. So this edge is supported because supported meaning it's connected. Supported meaning is connected. In the other ones, in the general sense, say that this point is connected with somewhere. This point is not connected, it's free, this longitudinal edge. So therefore, you have one longitudinal edge supported. So plate with one longitudinal edge supported, plate with two longitudinal edge supported. So basically, this table saying that this will falls in the flange, this will falls in the web. Yeah. So that will comes in the next one. So that's therefore we sometimes when you have this one, so you take it off these guys. But in here, we no need to take it off. Now, let's do the wave business now. Lambda E is equal to B on T. You know where this equation is coming from right now, because I show you that one, just before. Fy on 250. Now this B for this wave would be this one. This is B and this is T. So if I want to calculate this B, I can get this B from this one, 282 millimeters. So 282 millimeters thickness of the web is 5.5. Can you please do this one? B on T, 282 on 5.5. $51.27. Okay, we can confirm it here. 51.3. It's already given there. This is your B on T ratio for web. This is your B on T ratio for flange. In the exam test, you are happy. We are happy for you to take this one straight away without showing the calculations. But I just show it to you for confirmations. Does it make sense? All right. So 51.3, everyone happy to take it. FY 320, I just show it to you before, right? You can stop me if something is saying that, oh, this is where this coming from. Yes. Yeah, but both has 320. I agree with you. We can take the lowest, but both. Yeah, but yeah, you got 320 on both. Then you have a lambda E value. Can someone quickly do it for me? Lambda E equal to 45. Lambda EY. Can someone get it from the table? 58.01. Everyone agree with that one? And now we can just go back to the tables. Here, both longitudinal edge is supported, meaning that this is the wave. The longitudinal edge for the wave is supported here. Longitudinal edge wave is supported. This is the longitudinal edge. Another edge is supported. So this is a plate with two longitudinal edge supported, meaning two edges are connected. There is nothing free. So in that case, both hot roll lambda EY 45. 45, same business, lambda E, which is 58.01 is greater than lambda EY 45. Therefore, wave will buckle. Right? Wave will buckle meaning this wave will does this. Does this. So these guys here, we need to remove it because this one here, that's this one here, that we just need to take it off. Okay, because it's buckle. How much we're gonna take it off? Standards we're gonna tell us that effective widths we can calculate. That effective width equal to B on lambda EY lambda E less than or equal to B. So effective widths generally we will have a BE1 and BE2, but standards will just straight away give you BE1 plus BE2. So BE equal to B lambda EY on lambda E, we need to make a check. That should be less than B. So the B we calculated 282. Lambda EY is 45. Lambda E 58.01 less than or equal to 282. We will check. So can someone do this one? 282 times 45 over 58.01. 248.31 less than or equal to 282. Therefore, it is okay. Yes. Yep. 218 and 218 point something or 218 straight. 76. So that's good. You know what you done? Yep. Okay, that's all good. Then we continue. So effective width here that you get combine of this one is 281.1. So let's calculate the ineffective area, because ineffective area in the sense that this is ineffective area. Meaning when this buckling occurs, this guy gonna pop out. Pop out meaning it will does this. Right? So the standard say that you take it off this one. We don't want this part because it will not gonna contribute in carrying the loads because it's buckle. So how much it gonna come out? We can calculate that because this length is 282 millimeters. And this length from here to here, this length is 218.76 divided by 2. This length is 218.76 divided by 2. So we can just calculate this ineffective area. Ineffective area equal to 282 millimeters times by thickness is 5.5 millimeters. 5.5 millimeters. Take away these guys would be 218.76 times 5.5. So what would be your effective area? or something I done wrong. Probably 282. Let me draw up quickly. So these guys would be 282, take away 218.76. 282, take away 218.76. You get 63.24 millimeters. So these guys would be 63.24. So 282 take away, or you can just do it this way, 63.24 times 5.5. You get 347.82 millimeters square. I hope you understand that. I just calculate this ineffective width. Once you got the ineffective width, ineffective area, you can calculate the effective area. Effective area sense that this one. Effective area equal to gross area take away this 347.62 millimeters square. The gross area, we can take it from here, that gross area 4080 millimeters square. 4080 millimeters square, take away 362 millimeters square. You get 3732.38 millimeters square. So the KF equal to effective area on gross area 3732.38 on the gross area. Gross area we just calculated 4080. So 3732.38 over 4080, you get gross area 0.91. Sorry, KF. We can confirm it. Yep, 0.915. Frozen? Okay. Coming up? No, not yet. All right, let's connect again. Let us wait this system to come online. Therefore, I have two. But then we just frozen only one. ET219 it did not come. Yep, ET219, and it should come up here. It is there. Yep, it is there. So what I'm just saying that we just confirm this form factor 0.915, right, to the one still table. Now we can calculate this. Now we can calculate this NS section capacity. Now this NS section capacity would be KF AN FY. So section capacity NS KF AN FY. Now AN is the gross area when because we don't have any hole. Server Y said, what about local buckling? We already take into account local buckling. So 0.91. This is gross area 4080. And FY value is 320. So yes, please. Which one? Both has 320. Smaller value, please. 0.96 newtons and 1188 kilonewtons. Right? Any questions? All good? Or do you want me to stay here? Any questions before moving on to the next one? All good. All right. All right. Determining the design axial compression capacity of concentric is your axially. Concentric meaning axially. Loaded 200 UC 46 if the effective length of the buckling above the both axes is 3 meters. So we are talking about the now member capacity, like the long columns. There are two kinds of columns. One is a short columns and another one is a long columns. Some book also refer this one slender column. Some book refer this one as a slender column or long columns. Short columns meaning the size of the columns are short. Now someone might say, how do I know it's a short or long? Good questions. Because someone might say that, okay, it is 1 meter short, 2 meters short, 3 meters short. What is it depend on? The standards will gonna tell us short or long. I will tell you how. Okay, slender columns, but this is physically how it looks. Is thin and long. This is slender columns look like. But by the maths, we will tell whether it is a short columns or long column. I will tell you where when its times comes. I will tell you from the standards. Now, short columns generally have a failure modes of yielding or buckling. That's how it fails. But the slender column generally have these global buckling. Global buckling in the sense it has these lateral deflections. Because of this one, there is a factor called slenderness reduction factors comes into the play. Okay, because it's a instability. Instability meaning it's a long one. The long one, that's the longer the columns it goes, the capacity reduce. If you make a very long columns, its capacity, the penalty goes very high from the standards. The longer the columns you make, the larger the penalty you receive. Okay, therefore some engineers use the bracing. Then they said this is not a long columns, this is my land. So you can have a buckling occurring like this. So, but that's not a business here. So I'm just saying that this is the long. If it is 3 meters, it would be long columns as well. Now, what we're going to do it, we need to calculate both. First, let's say we will do this business, what we done NS, AF, AN, and I will not confirm with you because you know now. I will just take the form factor straight away. 200 UC 46. Universal column. 200 UC 46. Form factors. 200 UC 46. Form factor is 1. from the one still tables. Form factor is 1, gross area 200 UC 46.2. The gross area is 5900. 5900. The yield strength is 300, smaller between these two, 300. It gives me 1770 newtons, so it would be 1770 kilonewtons. Right, so that is your section capacity. Section capacity meaning the capacity of the short columns. That means capacity of short columns, right? But we don't know. We need to check both. Okay, in the case of if you go in the real design, we need to do the check for the both. Now we have two different length. Sometimes when you have a bracing, because let's say you have a columns. Let's say you have columns like this, and you can put the bracing on this side. But this other side, this side that you are seeing, this side is not braced. This side you have put the bracing. You can imagine that these columns has a restraint here. But if you want to bend here, that is nothing. The full length is that. So you can see this length is this effective length. So sometimes you might have a different length. Let's say length L1. This is also L1, but here we make it this is your L2 and L3. Right? This is your length. You got my point? That if you put the restraint, meaning that these guys will have a buckling happening in that one. So these become the short columns here, or not short columns, but the length is reduced. In here, there is no bracing on here. So if I want to bend this way, this is the full length. But here in the examples, they give you same length on the both sides. Right? So therefore, we no need to check for both. If you have a boat, because then you need to calculate lambda nx and lambda ny. How do we gonna calculate lambda nx and lambda ny? This lambda value is coming from page number 19, clause 6.3.3, lambda n. This lambda n is basically what is saying how long your column is. Because look at this, depend on your length. The length increase, this lambda increase. It is basically saying that this is the called what we call this modified member slenderness, meaning that how slender your column is. This is how the oscillants standard recognize that what is lambda n. Now, if you have a same length, because your lambda n could be different for both axes, lambda n x axis, lambda n on y axis. But if your has a both same, then it will go on by radius of gyration. Have you heard about radius of gyration? So this is the radius of gyration. It will go on by radius. The smaller the radius of gyrations, the larger the value, because it's inversely proportional. You can see here. So if you have a smaller radius of gyrations, you have a global high chance of occurring the global buckling. The equation for radius of gyrations is R equal to square root I on A. So it's about the resistance, about the moments, resistance about the bending, right? So the smaller the value, higher chance of getting the buckling, small resistance. Make sense? Huh? Which bigger number? Lambda n? Lambda, yes, the lambda n is correct. But this one smaller number is worse. Does it make sense or kind of? How? Kind of. The question is, how does smaller radius of gyrations make it worse? Make it worse meaning, let's say I give you two. Let's say I have a column here. They are appearing, they look the same, let's say. But this R value, let's say 5, and R value, let's say here is 10. This is bad. This does this. This one will do it, but not that much. You got it. But the questions comes here. Smaller value, the statements you understand that smaller value, you will get more buckling. But why? You understand why? Because so what happens here? You can see there is a relationship between R and moment of inertia. Let's say you have constant area, the area of the columns. But this I, that is the distributions about that axis bending. This is the moment resistance against the moment, resistance against the bending. If you have less resistance against the bending, I is less. Your geometry, the I is less. You have less resistance against the bending, smaller I. If you have smaller I, smaller R, meaning small resistance against bending. It is small resistance against bending. So the smaller value give you the higher chance of getting global buckling. So standards wants you to design for this radius of gyration. Thus, we can use the smallest radius of gyration when we have same length. Same length meaning about x-axis and about y-axis. Right. So let's for these ones, let's get the minimum of Rx and Ry. Minimum. Yep. Thank you. Rx is what? 88.2 and 51.0 millimeters. So we take it 51.0 millimeters, lambda n, Le on R, square root Kf. I will show you where this equation is coming from. Fy on 250. Effective length 3000 millimeters, radius of gyration 51 millimeters. These equations come from here. Gamma n 6.3.3. Basically, this equation is telling me how long your column. And here I agree with you. Larger this value, the worse it will get. Smaller this value, worse it will get. Larger this value, worse it will get. So you have 3 parameters that you can apply. And I will show you how the penalty is increasing. Now, Kf is 1. We say that this is 300 over 250, right? So if you solve this one, probably you will get 65, right? Any questions or any comments where it's coming from? Or it's not only for this example. I explain you how to use these equations and what each parameter is going to affect you. Now, another parameters we need to get it is called alpha B. The name of the alpha B is called member section constant. Member section constant. Right? How do we get the member section constants? There are 2 tables given in the standards. Table 6.3.3a and table 6.3.3b. If your Kf equal to 1, you can use this one. If your Kf equal to less than 1, you can use these tables. So you know how to pick between those 2 tables. We have hot roll universal column, so alpha B equal to 0. Right? You can read about those others, but these hot rolls, all the ones still are hot rolls. You know what is hot rolls and cold roll or cold form? What's the difference? Hot roll. Have you heard hot roll? Yeah, so you heat up the materials. That's correct. Temperatures plays in the role. So what happens when you want to create the shape? You heat up the materials. It gets soft, and then you make the shape that you wanted, like I-beam, circular, rectangular, whatever you want, and you can bend it or whatever the shape you want to get. That is the hot roll process. The cold form process, because you know some light materials, if it is too thick, then let's say for examples, if this is the page and the steel sheet is like this or aluminum sheet is like this, even with the hand, I can bend it the shape that I wanted, cold form process. But if I take this thick plate. I can't do it by hand, but I can heat it up and then easily I can do it and it will go. So this is the cold form process and hot roll process. The heavy sections, like the thick and strong sections, they need to do the hot roll process. I hope you understand that. This is the simplest things I can explain, or not really. Right, so that is the hot rolls, but that is not a story that we need to cover. That is just additional information. These standards assume that you know what is hot roll. All right, so this is hot rolls, and we have a alpha B value equal to 0. So we have alpha B equal to 0. Now we can come back to these tables. Look at this. Now I promise that how the standard is going to tell you whether it's a short columns or long columns. Here you go. Look at this. When your gamma n value is 5, you have only 1. There is no reductions. 1. Meaning this is short columns. This is short columns, short columns, short columns. Immediately when I have 20 and when you have this 0.5, you get 2% penalty because you are long columns. Global buckling occurs. So you can see that. So this is how you can say that whether it's a short column or long columns. The more longer you get, this is short columns. So the length increasing or radius of gyration reducing, the penalties are increasing. Look at that. The penalty sometimes your capacity almost becomes 0. There is no columns here. Look at this one. Last one, 600. The longest columns in cases they already put just 0.00. There is nothing. If you have 100 and you multiply 100 by 0.022, what do you get? Nothing because of this. What's the point of using it? That's right. Therefore they say that they give you the warning. Sometimes that if you use this, sometimes they use this slender section, but if you have a capacity, let's say very high, sometimes they, let's say 10,000 kilonewtons, then you get 220 kilonewtons. So not so there is a way that is a warning here. Yeah, sometimes architecture wants it, but that would be expensive process. Right? Yeah, just look at this here. This in the middle is doing nothing. Doing nothing means the student who is sitting over there, they can't see my screen. The half, I can't use the full classroom if I want to use it because of these columns. So architectures will gonna tell, and if this is happening for every, if I come to the similar one, I will tell my architecture, don't put this one. Whatever you want to do it, because you are providing the space to me. Someone might say that this office has this meter by these meters, let's say 25 by 25 or whatever, 100 meters square. But I'm not counting 100. It is by on paper is 100, but I would say it is 50 meters square. It's not value for money. So structural engineer has a job that, okay, how do you gonna remove these columns and put it somewhere that will not come in the middle? It's a massive. That's not a part of this subject, but that's just just you raise architecture things, but that's the other business. Okay, so that is just things. So I think how much lambda n we got? We got alpha b value equal to 0. So we will just going to follow this one, huh? Lambda n 65. So you happy for me to take 0.779? Lambda n 65 on page number 92. 65, 0.779. Still, we got about 22% penalty because of 3 meters long. So we got alpha c value equal to 0.779. So NC, which is given here, NC equal to alpha c close 6.3.33 alpha c ns less than or equal to ns. Alpha c ns less than or equal to ns. Alpha c 779, ns is 1770 kilonewtons. So you get 1379 kilonewtons, and if you just want to get the reduction factors, 0.9, 1379 kilonewtons, 1241 kilonewtons. Where these reduction factors comes from? Axial compressions, and that is come from 0.9. Yes, please. Where is the equations? All these ones that you can see here, they already done it for you. Yes, that's how you do it. But if you want, tick, 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 this is all there. Plug in Chuck, and you got it. Yeah. All right. Okay, here. Alternatively, value of the member centeredness reduction may be obtained directly from the tables. This one written line there below. Right? They say that using the value of modified center and the appropriate member of standardization, this one alpha B and this one. It says alternatively. So we just use this one, but this is a long process. But they already done it. All right. Any questions? All right. Now you're going to see the different length. You're going to experience the different length now. In the last one, I will not repeat what we done. I think the changes that we are going to do it. Axially loaded compression members. Restraints such that effective length of the buckling is 6 meters. As I mentioned, sometimes when you have a columns, let's say this is 6 meters, and you put in this end the restraint. So this side become 3 meters and this side become 3 meters. I hope you understand that. Right? So one side you put the restraints, another side you don't put the restraints. So that's how you make it 6 meters and 3 meters. If the service dead load and live load is given, so dead load G is 500 kilonewtons, Q is 300 kilonewtons. Determining the effective universal beam section. You might come across with two kind of questions in holes after week number 4 after the wind loading. You have two different scenario. One is the analysis questions. What is analysis questions? That the beam sections will be given to you. Let's say UB given, UC given, parallel flange is given to you. Someone said take this and then calculate the capacity. Another one is a design. They give you N star, like what's the load coming on to, or M star or V star. They give you the design load and you estimate what is UB and what is UC. So these examples, the previous two example was analysis. Already the universal beam, universal columns, and all these cross sections given to you, length is given to you. But here they have not given you the universal beam and universal columns. So we need to estimate. So we need to start with something. Did they mention anything? No, they say that universal beam. And he says that word efficient. So someone might say that, okay, you told me to do the universal beam. I can go in the universal beam and pick the biggest one. What's that about? Because sometimes you have all this one is the grade 300. Sometimes you may get the cross sections, which is you can buy 500 megapascal steel, the universal beam and universal column. Not this on these sections. There are another suppliers that you can purchase the 500 megapascal. This is 300 megapascals. Now grade 300 meaning that you need to use these 300 megapascals your yield strength. 320 also falls in the 300 megapascals range. Grade 300 meaning within that range. The Australian standard said you need to produce the 300 megapascals, but it can be 320, 300. Grade 300 meaning that the generalized strength of the one. All right, now now we can calculate n star. N star equal to 1.2 G plus 1.5 cube. Someone might say, where this coming from? If you go back to the strength weeks 1170.1, you have this. I think it's a part 0. I forget to get the part 0. Do you, someone has a part 0? Yeah. Yes, you got it. But for the completeness, I can show it on the screen. Here you go. 1.2 G plus 1.5 Q. Page number 16, 1170.0. Okay, that is for the strength one. All right. Thank you. Now here you have 1.2 dead load. 500. 1.5, 300. Why do we multiply this 1.2? Why not just make it 500 plus 300? Because that's the load given to us. It is 800 should be. If I do this once, it would give me 1050 kilonewtons. We have extra 2050 load. Service limit, service limits, we just not do service for, this is the for service, we just do this short term. This is service load. Yeah, this is ultimate strength. So why do we multiply 1.2 and 1.5? You know what I mean? The questions, because we would take 800. Yeah, that's right. So it's just the safety factors, because the standards wants to because that's the estimations. You know, this 500 and 300. This is just a guessing business. Right, the surveyors going to tell you how many going to use it. But that guess business, of course, you will think in your benefit. You will not gonna guess higher because it will cost you more. Let's say you want to make a university, and someone wants to save money. Someone might say, in this room, you will not gonna. I know, but we have 50 students, but we will get 10. 1, 2, 3, 4, 5, 6. Said, okay, don't worry. And then standard said, okay, I know what you're going to do it. So let's 20% for your dead loads and make it 50% agra for live load. Right? In the USA, the bridge was collapsed because there was a you know, this S plant, that's the road, that black stuff that you make it. They done the repair so many times. Every time they go on the bridge and see some damage on the road, they put the new layer. After a couple of years, they find the damage, they put the new layer. Keep putting the new layer, the bridge collapse. Why did the bridge collapse? Because of the dead load. Because you keep increasing the dead load, and that bridge does not design for that kind of particular dead load. So therefore, this is just extra. Okay, anyway, that's not a business. But now we need to make an assumption that alpha C equal to 0.7. Now some students said, "Ooh, that is kind of where is coming from." We did not see that. Right? Because that is the assumptions that we need to try. Why we need to make an assumptions? Because we need to start somewhere. We don't know where to start. So we assume that 30% penalty will come. Someone might say, where is 30% penalty will come? Look at these ones. In the previous examples, we have 3 meters long. We have 3 meters long. We have now 6 meters long, I know, and 3 meters. So we got about, look at this, 28% penalty. How much? 22% penalty here. So it's 6 meters. We might say, okay, let's make it 0.7. Now, someone might say, when you do a lot of calculations, you will develop these skills. Someone might say that, okay, what about the test? Don't worry about the test. We will tell you what alpha C value. You don't need to make an assumptions there. But just for the engineering skills and knowledge, the engineers make, when they look at this one, approximately they can estimate this 30% penalty will go from the global buckling. Right? This is long column. So that's the assumptions. So once I make these assumptions, alpha alpha C equal to 0.7, we can calculate this n star equal to 5 NC. Where this coming from? N star equal to 5 NC. So 6.1 on page number 87. Your capacity should be greater than or equal to your demand. Okay, I just for maths purpose I take it equal to. Okay, so that is n stars. I think we got the n star value 1050 times 1000 newtons. These ones, you know, 0.9. NC, we get alpha C, NS, right? NC, I can show it to you again. NC, alpha C, NS. NS, KF, AN, FY. One 050.7, we assume KF, AN, FY. 1050.9, 0.7. Let's assume KF1. Gross area we need to find FY 300. So if you simplify that, 0.9, 0.7, 1, 300, you might get the gross area of millimeter square. So this is just why I quickly run through. This is just a rough calculations. This is not accurate. I quickly estimate that I might need 5555 millimeter square to fulfill that demand. 10. How much the demand was? The demand was 1050 kilonewtons. I might need 5555 millimeter square approximately. So if you go to that one in here and go find the gross area which is greater than 555, you might get 5720. That's close. 360 UB 44.7. So we can try with that one, right? Because we have 555444 is the gross area that's required, and we can just pick a little bit extra than this one, 5720. Again, this is gonna be try. We don't know whether it's gonna satisfy or not. So that is 5720. So let's try. Let's try 360 UB 44.7, which has a gross area of 5720 millimeters square, which is greater than your required one. Therefore, we choose it. Okay. Now we can do all this business on these ones and see if the capacity is greater than 1050. If the capacity, which is 5 NC of this one, would be greater than your N star, we are okay. If not, then we increase the size. All right. So for these ones, what is KF? 360 UB 44.7. 0.93. Thank you. 0.93. What is the gross area? Oh, 5720. We got it. 5720 millimeter square. What is FY? We take it 320. So let's calculate first this NS. here from here. Let's calculate the section capacity first. NS, KF, AN, FY. NS, KF, AN, FY. KF equal to 0.93. Gross area 5720 millimeters square. 320 Newton per millimeter square. So if I use the calculator, you get 1702 272 newtons. 1702.272 kilonewtons. Right? Now we need to calculate this because it has a different length, which is lambda nx, length of x over rx, kf, fy is 320 on 250. Right? So length of x in the x direction is 6 meters. So 6000 millimeters. Rx 146 millimeters. KF 0.93. 320 on 250. You get lambda nx value 45. If the same length, we go for small or big radius of gyration. If there is the same length, smaller radius of gyration, right? But here we don't have small length, so the smaller radius of gyration will not going to help us. Lambda ny is same thing. Length about y-axis given in our examples, which is 3 meters. So we can make it 3000. Ry 37.6, right? 37.6 kf 0.93. You get 87. Now, which one we choose, 45 or 87? Why? That's right. So we choose the worst numbers. We don't want to design for something that is lower. The lower, this will give you the attract higher penalty. I know we don't like it, but this is how we need to make it safe. Yes, please. Yes. Because different radius of gyration. Look at that. Therefore, the radius of gyration also play the role, not only the length. Therefore, I give you the theory. I spent 10 minutes. The business of radius of gyration. Smaller radius of gyration, small resistance against the buckling. So look at this. This will have a higher resistance. Yes. Yeah. So how this radius of gyration and moment of inertia? I understand your question. So look at this, guys. This is the typical things. Let's say this is your x-axis. This is your y-axis. Now, this radius of gyration of moment of inertia is based on how the materials are distributed from your axis, how far, and how this one. So look at these guys. This one, larger area are distributed from the x-axis. Look at these guys. sitting far from the x-axis. Far from the x-axis means if I sitting close to here, then small moment of inertia. The distribution of the materials from the axis, that's how you do. So this is larger moment of inertia, right? So look at the other side, that if I have this y-axis, look at the materials distributions on the other side about this axis. This is how you got the moments. The larger, so if you have an axis here and you put the materials here far from this one, somehow you have large I moment of inertia, large resistance against bending. Same thing if I put the material close to this axis, same materials, by the way, same size. Let me do the same size to have more. So let's say same size, just assume that is same. Small I meaning small r, meaning large r. So therefore we have different Rx and Ry. And this is how you're going to rectify where is a weak axis and a strong axis. So in this case, your y-axis is weak. The global buckling will occur against the y-axis first. Of course, it's going to occur for the x-axis as well. I'm not saying that it will not going to occur, but the first, the give up is the between x and y-axis. They're going to talk with each other. Who's going to go first? Y-axis said, I will go first. I will buckle first. You come later. All right. Does it make sense? This is the simplest things it can go. Because these things in the mechanics of solid, it should be clear at that stage. I would not supposed to give you the lecture on I and R. You said, no, I'm just joking. This is when I was like you, it's not going to be happen. So I need to explain you, but I think you know the business now. Yeah, but at that time, you never know what is moment of inertia and what is gonna go it and where it's gonna useful. You just blindly calculate moment of inertia for that kind of things. And you understand the radius of gyration now? Okay. All right, so everything is clear. So we will gonna use lambda n equal to 87. Alpha b equal to 0. Everyone knows now because it's kf is less than 1.93. Kf is less than 1.93. We are using universal beam or something. We have alpha b value equal to 0. So alpha b value equal to 0. So we're going to follow this one, and we have 87. Probably we need to do the interpolations between these two. 85, 0.645. 85, 0.645. This is lambda n. This is alpha c. We need 87. How much x? And we have 90. We have 90. And for 90, we have 0.610. 0.610. The interpolation business 90, 85, 0.610, 0.6645 equal to 87 take away 85 on x take away 0.645. So x take away 0.645 equal to 87 take away 85 over 90 take away 85 times by 0.610, 0.645, and then you just do plus 645 plus 0.645. Can anyone do it? Make sure that it numbers should be counts between these two numbers, 0.645 and 610, right? You don't cross those limits. 0.631. All right, so this is your alpha C value, right? Just we done the interpolations. Now, once you know this alpha C value, then you have a this NC equal to alpha C NS, NC equal to alpha C NS 0.631. Look at the penalty. Keep an eye. We assume 0.7 penalty. It was not 0.7 now. It become 0.37 almost, right? 0.37. So we assume 0.3. That happens. We can't just gonna go on spot on. But let's see. NS we calculated 1702.272. 1702.72 kilonewtons. So this one here we going to get 10 0.13, right? All good. And then you multiply by the capacity factors 0.9, 1074.133 kilonewtons, 967 kilonewtons, 66, so 68, let's say. So then it is less than the requirement, which is 1050, I believe. Not adequate. Not adequate meaning these guys, which is we assume which one is assume. We assume try 360 UB 44.7. 360 UB 44.7 not adequate. What does it mean not adequate? The standard saying that it will gonna fail at 968 kilonewtons and you are pushing at 1050. Not good. Right? So your demand is 1050 kilonewtons, but the capacity of your member is 968 kilonewtons. It is not allowed. You should have a capacity more than 1050. So select the sections which would be so we tried this 360. So let's go one more above. Yes, we can do that. 310 UB 46.2. That's also possible. We can try 310 UB 46.2. 310 UB 46.2. 310 UB 46.2. And what was the gross area for that one? 5,930 millimeters square. And what was the gross area that we got? We got 5720, right? Yeah, that was the last one, 5720. Yeah, so in here we might be able to do it. Gross area. The KF is what for this one? 46.2. KF is 0.991. Gross area is there. Yield strength 46.2. Yield strength 300. So NS equal to 0.991 times by gross area 5720 times by 5930. Yep, 5930. 5930. So what we're gonna do it here, 0.991 times 5930 times by 300, you get 1763 kilonewtons. Now we need to get all this business. We need to get this Rx and Ry. The 130 and 39. They will have a trouble. 130 and 39. 39. I think these numbers are smaller. So the smaller numbers is better. So if we do these calculations here again, for this one here, how much it is? 130 and 39. So here lambda n 130. Here you can put 130. This one kf, we can change it. Lambda x 130 kf, we need to make it 991. $6,000 divided by 130 times by kf would be 0.991 times by square root 320 on 250. You get 52. Ry, we can use 300. So let me quickly plug in 3000, 50 point. So let's say 50. And in here, can you please quickly do it? And this one, 84. And we change these numbers as well. So 84. So for that 84, we can do the interpolation here. Right, these numbers will stay same. Change it to the 84 here. Oh, we can't use this because you have 85. We need to take the another one. Between 80 and 85, 0.681. So 80, 0.681, 84, and 85. 85 is 0.645. So what would be this one? Um, 85 take away 80 on 0.645 take away 0.681 equal to 84 take away 80 on x take away 0.681. So in that case, it's just a repetitions, by the way. 84 take away 80 times 0.645 take away 0.681 over 85 take away 80 plus 0.681. Can you please do that? So alpha c value this one, and straight away we multiply by ns. Did you get any answer? $0.652. Okay, so that's 0.65, and you just multiply by this 1763 times 0.622. 1763 times 0.622, you get 1096 and times by 0.9, It does not work. 987. So we need to go one more higher. So we can try 360 UB 51 or 44.7. 50.7 we can go. We can try 50.7s. And for that case, your gross area would be 6470 millimeter square. We got KF value of 0.963. We got RX value of 148 millimeters. RY, you can extract all these informations from your one steel tables. And since all these values are higher, what you can do it, we can just calculate the capacity between these 6470 and in the previous one was 5720. And the capacity was 967. So you can just take the ratio. So that ratio was 5720, and that will give you 1094 kilonewtons, which is greater than your 1050. Therefore, we can take which one? Yes, if it is all the values are larger, the condition is all these numbers should be higher. In the previous one, there was not higher. Probably one of these RX and RY was smaller. Therefore, I did not do this one in the previous one. Ratio what? So you got 1096. Oh, by just going over. Yeah, but 1094 conservative. So still I'm winning. No, sorry. No, that's pretty close. No, that's what. All right. Yeah, I hope it is fun. This exercise trigger some useful informations. Now, last one. We have take a lot of times. So now I'm not gonna go all these in the great details. You know the business now, right? So let's say you have a parallel flange channels. I can show it to you parallel flange channels, PFC, taper flange beam, parallel flange channel, right? The C channels like this. All right, what was the 300 PFC? So we are working on 300 PFC. We are working on here, second row. Right. Now here they say that we need to toe-to-toe compound box and concentrically loaded columns. Effective length of the buckling about both is 6 meters. So we will take smaller radius of gyrations straight away. Would helpful. Determining the design capacity of the compound column, compare design capacity of single PFC for the same effective length. So what they say that they will two plane channels. There is a one, there is another one. They take it and they weld it. This one is to make a cross sections, and now they done the axial loading. And then they said, okay, you need to find a capacity for single one as well, and then compare both. Right? So the business is simple. That we can take the gross area for this business. We will have a gross area of 5110 millimeter square, but we have two. So gross area for two would be 10220 millimeter square. IX, the radius of gyration about the x axis, 72.4. millimeter to power 4, but we have 2. So 72.4 millimeter to power 4. It gives me 1448 times 10 to the power 6 millimeter to power 4. And there is a 10 to the power 6 here, and there is a 10 to the power 6 here. You got it so far? We just multiplying 2. Radius of gyration about x-axis, Ix on gross area. So 1448 point. Radius of gyrations. Let's check it. 118.5 10 raised to the power 6 over the gross area is 10,220 millimeter square. We might get 144.8 by 10 to the power 6 divided by 10,220. Square root answers 119. Okay, that's the radius of gyrations about the x-axis. Now radius of gyration about the y-axis. Radius of gyration about the y-axis. So you know this y. So about x-axis meaning this ones. About the y-axis, this is the x-axis. About the y-axis. So if I want to calculate a radius and gyration about y-axis, Iy over a. Yes, please. Yeah, mathematically you multiply by 2 on both sides, cancel it out each other. Yes. So then it becomes same. So the radius of gyrations are about the materials that you are distributing from about the x-axis, that I, and area is same. So therefore we get the same numbers. 1. Yeah, if you're confident, you can take 119, but just to make sure verify that sometimes it get tricky. But you know how to get that number, and that match with the constant. So Ry, so Iy, you know this box, you know how to calculate this Iy. If you take, if you just find the centroid and then you calculate this I and all, but I think there is the easiest way that we can do it. So the Iy value equal to Iy for your one plates, which is given here. Iy is 404 times 10 to the power 6. You know Iy, I plus AD square. So I for your section is 404. 4.04 times 10 raised to 6 millimeter power 4. That is coming from your one steel tables. Gross area is 5110 millimeter square coming from here, and times by the distance square. So if you just get the distance, there you go. The width of your flange 90 millimeters. So 90, that is from here. Take away your centroid 27.2. That's, I can show it to you here as well. That is your coordinate of the centroid 27.2 square. So if you just use the calculators, 4.04 times 10 to the power 6 plus 5110 times 90, take away 27.2 square, you get 24.19 times 10 to the power 6 millimeter power 4. We have 2, so multiply by 2, you get 48.39 times 10 raised to minus 6 millimeter to power 4, and Ry equal to square root Iy on area 48.39 times 10 raised to 6 millimeter power 4 on the area, gross area 1020 millimeter square. You get the Ry value of 68.8 millimeters. Same length. Who is the winning? 119 smaller. We're going to take it R equal to Ry 68.8 millimeters, right? Yes. Yeah, because we have this. And then Iy value, if this is my y-axis, and then you have this, and your y-axis is here. They are quite different. You can't take it. Yeah, because this is the compound sections that we want to take it. You need to find the centroid and then how we're gonna go on the y-axis and then so on. So Ry equal to 68.8, Kf equal to 1. Let's check. Kf equal to 1, that's fine. Gross area equal to 10220 millimeter square. So NS equal to Kf 10220 millimeter square times by 300. So we get 10220 times by 300. You get 3066 kilonewtons. Right? Gamma n length is 6 meters. 68.8 smaller value. Kf1 300 on 250. You get 95. Alpha B 0.5. I can show it to you because that is quite changed. Hot roll channels. I think this is a hot rolls one because the one still one is a hot rolls, and Kf equal to 1 and 0.5 for the hot rolls channels. Alpha C 95 and 0.5. 0.5, 0.5, 95, 0.515. So in that case, NS, NC, 0.515 times NS, 3066 would give you 157 kilonewtons. Look at that, how much it is wipe it out. You told me that, remember 0.0002, that's effect is come here. You told me 0.002. We have a 3066. We just get it to 157 because of that. Oh, yep. 1579. Sorry, but still half is half gone. Now you just multiply by 10%. So we got 10% again gone is 1421 kilonewtons. So that is your capacity for compound. Now we need to do it for one, right? You remember that is for one. Now for a single one, again lambda ny is the winner. Then you have 6000 and 28.1 Ry. I can show it to you. Ry is 28.1 times by Kf is 1 times by 300 on 250. You get 234, right? Look at this, 234, very high penalty. Your alpha value got 0.127 here. How much was that? 234. We got 234 here, and alpha b 0.127 because I think 234. Just we need to make it interpolation here. So here 234, and we need to make it interpolation 0.127. So that is alpha c. So your capacity would be 0.1 to 0.9 times 0.127 times by your NS. You can calculate. KF is 1. 5110 is the one channel. 300. So you get 1533 kilonewtons. 1533 kilonewtons. You get 1533 times 0.9 times by 0.127. You get 175 kilonewtons. Look at that. So your capacity is your have a 1421 kilonewtons for when you have a double, and when you have only singles you have 175. So 175 over 1421, you got 12.3% multiplied by 100. So the capacity is 12.3% when you weld it together. All right, I hope it is helped.